Hi, my name is Wesley Black. I'll be presenting a paper called FirmWire, Transparent Dynamic Analysis for Cellular Baseband Firmware. This is a paper by Grant Hernandez, Marius Minch, Dominic Meyer, Alyssa Milburn, Shinjo Park, Tobias Shanowski, Tyler Tucker, Patrick Traynor, Kevin R. B. Butler. What is a baseband processor? I'd like to give a little bit of background on what a baseband processor is before we get into the paper. A baseband processor is a dedicated processor that is running a real-time operating system. It handles cellular protocols, message formats, and state machines, and they typically run on high-performance firmware. But they can also be pretty difficult to analyze and test. This is because they are complicated and are run in secured mobile devices, and it is in addition to them being proprietary to whatever company wrote it. And the baseband processor is typically paired with an application processor, where the application processor will handle a phone's operating system and apps. The baseband processor handles all the networking. Previous research has also shown that exploiting baseband processors is possible, and that the automated testing of basebands have had differing levels of success. So before I move on, I'd like to think what are some possible ways that you could automate the testing of basebands? So continue on, we give some background knowledge on some of the ways automated testing has been done with baseband processors. So security testing has had varying degrees of success because basebands had been treated as black boxes during testing, and the tests were done over the air. So it was pretty hard to scale. You had to get more phones, more devices set up before you keep testing them. And because it was treated as black boxes, you couldn't really see why something was crashing. You could just see that it crashed. So it wasn't very easy to classify the types of crashes. But moving on to some newer approaches, they were one of two ways that were typically taken, either emulation or static analysis. Emulation could test individual parsers, but it typically failed to capture interactions with other areas of the firmware, and had issues scaling when presented with the large number of functions that exist within the baseband's firmware. Static analysis ended up having a lot of false positives as well. In both cases, and both approaches, issues from how the baseband processor interacts with different components couldn't be found. This was because both approaches typically ignored most of the other parts of the firmware. I'd also like to give some background knowledge on what fuzzing is. So fuzzing is an automatic testing technique commonly used to find security vulnerabilities and bugs. A fuzzer creates a test case for the program to execute initially. It then waits for something unexpected to happen, such as a crash or a hang-up or some unexpected behavior. If something is then found, it'll save the input for the developers to analyze. It might save extra logs or some function calls. But if it survives, the fuzzer might then generate a new input and repeat, and if it dies, the fuzzer will generate new input and wait for something unexpected to happen and just keep going. So, based on some of the background knowledge I gave earlier, what could be some of the motivation the authors had for wanting to create FirmWire? So, since the baseband processor is responsible for all of the cellular network functions, being able to understand and ensure that the baseband processors are secure is pretty important. But it can also be pretty complicated with existing solutions, since baseband processors tend to be complex. They don't have a lot of testing platforms, and the existing solutions already fall short. And some of the already existing ways to analyze the baseband processors all have their own methods and shortcomings, like dynamic on-device testing, which performs the test physically by actually sending the messages on the actual user devices and observing what happens. But it only offers limited insight to how the device's interstate is, and even with monitoring baseband diagnostics, you could need a rooted device, which may not even be allowed by the vendors selling those devices. Then there's emulation-based parser testing, which just pulls parsers embedded from the baseband to test them, but it requires manual effort to pull it and can fall short when trying to find bugs. Finally, there's also specification-driven static approaches, which try to find bugs by looking for mismatches between the actual baseband implementation and the specification. But that doesn't work very well either, because it can find bugs that can't actually be reproduced on real devices because it ignores context or states on the device. So, what is the threat models that the authors are assuming? Well, the authors assume that the threat against a baseband processor is going to be coming from an attacker who is taking control of a base station. This allows the attacker to craft payloads, whatever payloads they want, that will be processed by user equipment. They assume that the authentication between the base station and the user equipment has not yet been done, in order to show us that these attacks can be performed upon real devices that don't need to have been pre-authenticated. The authors mainly focused on LTE, and since some devices can use GSM networks if those are available, either due to attackers or because LTE is not available, the authors also looked at GSM in addition to LTE. So here we get to a slide with an actual image, and we're going to be talking about FirmWire's design. So the authors wanted to ensure that FirmWire could be scalable for many different images, and be able to view the states at the beginning, and that it would be capable of emulation. So looking at the image here, it's the overview of how FirmWire works and FirmWire's platform. What it does is it starts by taking in a baseband's firmware, and this goes through the vendor-specific plugin. And what that plugin does is it abstracts away the image-specific information and makes that abstracted information available to the emulator. Now, the vendor-specific plugin does require some manual effort to set up by the user in order to get it ready, get all the information abstracted, but it only has to be set up once and it can be used again. And not just can it be used again, but it can be reused for a lot of different images as well. Once it goes through this vendor-specific plugins, it goes to the emulation core. What that does is it runs the firmware itself. It lets the fuzzer do the automated analysis and run it, and interacts with everything else going on. When it discovers a crash, it can be ran out to logs and let an analyst go ahead and see what happened and run it into a base station so that an actual device can be tested with it to ensure that the actual exploit exists. FirmWire also allows for peripherals to be added in, especially since some firmware images need to have additional peripherals to actually work. They created some peripherals and have some preset peripherals for users to use, and they did note that if a peripheral has to be added, it's pretty simple to do. So how would you analyze the firmware to ensure that you're actually getting good crashes, finding actual vulnerabilities? Well, what the authors did was that they used coverage-guided fuzzing, and they made sure to fuzz the protocol implementation from within the baseband. and so they would follow the rules of the baseband processors. This meant using the correct APIs so that any false positives due to the uninitialized states would be avoided, so they could actually get to a good state that would be seen on an actual device to start with. The authors started by using hooking to record the arguments and return values of any of the API calls. This made it easier to conduct root cause analysis on any of the crashes going on, and to make it even easier, the authors also integrated their tools with GDB. So the image here shows the overview of G-Link, which is how FirmWire allows for host to guest and guest to host communication by injecting in a guest link module. This allows the host to inject arbitrary messages and other events into the baseband from scripts, and allows the host to receive back from the baseband. To demonstrate FirmWire, the authors chose to use 9 phones that contain baseband processors from Samsung and MediaTek. The chosen phones were Galaxy phones, the specific versions of which can be seen in the image. The authors were able to support 4 Samsung basebands processors across 7 phone models, and were able to boot about 200 firmware images on those 4 Samsung basebands. They were also able to provide 17 peripherals for use with the Samsung baseband processors. For the MediaTek basebands, the authors were able to support 2 of the MediaTek baseband processors across 2 different phone models, and they were able to boot about 9 firmware images. And they were also able to provide 12 peripherals for use. They noted that with the MediaTek basebands that they needed to set up the application processors to have an interface with the baseband processors, because the baseband processor would get some startup information from the application processor. They're also able to get FirmWire to set up an initial state by emulating the whole baseband, and they're able to get it to reach new states through their testing. And they're able to set up their anomaly detection in FirmWire to detect faults as well, based on specific conditions. And so it can save the lead up to the crash or the fault to allow an analyst to view exactly what happened for the crash or issue. Now, what are some of the reasons that the authors might have chosen only to use the Galaxy series of phones instead of also looking at iPhones or some other types of devices? The authors do mention later that they have issues with some of the baseband processors because of how proprietary they are. For example, some Qualcomm baseband processors will have their own ISA that makes it very difficult to emulate. So now we move on to evaluation. And I'm going to ask you the same questions that the authors asked themselves. So first, can a dynamic emulation platform aid security testing for baseband firmware? Well, they found that, yeah, it can. They found 7 vulnerabilities in the baseband firmware, with 1 vulnerability they already knew about and that they used to test FirmWire to make sure it was finding the vulnerabilities. They also found 4 vulnerabilities in the LTE radio resource control, 1 in the GSM session management, and 2 in the GSM call control. And of those 7 vulnerabilities they did find, 4 of them were unknown vulnerabilities, pretty much newly discovered. The specifics of these vulnerabilities can be found in the paper, which I encourage everyone to read. So we go to the second question. Is FirmWire's approach scalable? So the authors found that yes, it was pretty scalable. Do you remember in the last slides when I was talking about how they were able to set up a couple different emulators to cover hundreds of different images? Well, the authors went a little bit further with that. They downloaded 229 unique firmware images, and without changing firmware at all from how they had it, they checked how many could be easily booted up with no modifications, no changes, not fixing any errors, just right away. They were able to boot 213 of those unique firmware images, with the remainder just having issues that could be fixed, such as having missing peripherals or just entering an infinite loop somewhere. Final question they asked themselves: are vulnerabilities discovered with firmware actual bugs affecting physical phones? Remember how part of the firmware's design was to be able to write out what happened in the lead up to the crash so that an analyst could test on a real device? Well, that's what the authors did. To reproduce the results from FirmWire, the authors went ahead and took those Galaxy phones and went ahead and reproduced those vulnerabilities on those phones to show that yes, indeed, FirmWire is finding actual vulnerabilities. So the authors also wanted to compare FirmWire with some other fuzzers. So before they compared it, they looked at the code coverage of FirmWire itself, and they found that it was pretty low code coverage overall. The LTE radio resource control tended to have the most code blocks executed, but then the GSM session management and GSM call controls ended up having less code blocks executed. And so overall code coverage was pretty low. The authors stated that this was primarily due to the fuzzers targeting a very small subset of functions because of their threat model, an attacker having pre-authenticated control. And so not a lot of functions could actually be reached by the attacker. So they looked at two state-of-the-art fuzzers, LTE Fuzz and Base Safe. LTE Fuzz did not have available source code, and running it, the test durations were not actually recorded with LTE Fuzz, which meant that comparing LTE Fuzz and FirmWire was going to be pretty difficult. The authors decided instead to compare FirmWire with Base Safe. They found that creating manual harnesses for Base Safe to run the fuzzing resulted in less code blocks being executed than with FirmWire. But what they did find that was interesting was that if they wrote a wrapper to automatically take memory snapshots from FirmWire to be fed into Base Safe to create the fuzzing initializations and fuzzing hooks, that Base Safe, with these automatic initializations and the automatic hooks being generated and taken from FirmWire, it was able to get the most code coverage than just using FirmWire by itself or just manually setting up Base Safe by itself. The authors pointed out that because of this interesting thing, that FirmWire could be pretty useful for integrating with other tools that are being used for fuzzing. So now we move on to some of the issues that the authors found. So I mentioned one of them earlier, Qualcomm. Qualcomm, despite being the largest baseband processor vendor, was not included in this. This is because Qualcomm uses its own ISA, Hexagon. There's not a lot of documentation about Hexagon, and that makes it difficult to support in FirmWire. The authors did point out, though, that if an emulator for Hexagon was made, then it could be pretty easily integrated into FirmWire. But since there is no emulator that can be easily used, then it's not very easy to create one and set it with FirmWire. The authors also noted that the cell protocols tended to be very stateful, and that although FirmWire does start off in initial state, the number of possible states does make it a lot more difficult to explore all of the possible states and reach into different areas. it's also difficult to test any of the found crashes, because although vulnerability detection was automatic using fuzzing, they still have to take those results and actually test them with actual devices and actual phones. And it's even more difficult to test older versions of firmware because there are anti-rollback protections on some phones. And since you have to do each of these tests manually, it can get pretty tedious and pretty time-consuming to set up the specific devices and the specific images that are being used. So what are some of the directions that FirmWire could be taken further into? Well, the authors point out a couple different directions that could be taken. Starting with 5G, they noted that the changes made to support 5G seem to mostly just be hardware, a different processor, and a completely different memory layout. But they observed that the operating system being used, Shannon OS, was pretty much the same as before, and that a majority of firmware could just easily be applied to 5G and require minimal setup. Another direction that they looked at, that they talked about, was setting up more peripherals to explore how baseband processors would interact with them. One example they gave was setting up a GPS peripheral to see how baseband decoding GPS might reveal new attacks and vulnerabilities. Another way would be to integrate FirmWire with existing mobile emulators. Currently, when you're testing calls and texting, they'd have to be tested on either real devices or just with substituting the baseband processor with something else. Adding in FirmWire could allow for more accurate and faster tests, because then you don't actually have to get a real device each time you want to test the calls and text. You could integrate FirmWire, let the device be emulated, and perform faster tests. So, in conclusion, what is FirmWire? FirmWire is an emulation platform for baseband processors that allows for fuzzing and automated testing of the baseband's firmware. And they're able to confirm that FirmWire does indeed scale up favorably, and that FirmWire could outperform existing fuzzers. But not only could it outperform existing fuzzers, but that combining FirmWire and existing fuzzers together resulted in much greater code coverage than by themselves. And using FirmWire, the authors were able to find 7 different vulnerabilities, with 4 of them having been previously unknown vulnerabilities. And not only were they able to discover these vulnerabilities, but they were able to confirm that they existed by manually testing them with Galaxy phones. So, thank you for watching this presentation, and please check out the paper presented here. It's a pretty good and a pretty interesting paper.